As usual, I forgot something in the last video. I wanted to mention the Leonard-Jones potential, and the Leonard-Jones potential contains two terms. It contains a term for the attractive interaction due to the van der Waals forces, so that is W of R equals minus A over R to the sixth, plus some repulsive component that is given as usually something like B over R to the 12. So what that means is that as particles get closer and say they're interacting by van der Waals force, they get closer and closer and the energy is going down, down, down because of van der Waals force, and then they get too close, they get really close, and then they push away. And that is the huge energy at very small r's, where we have the 1 over r to the 12 term that blows up. So when r gets really, really small, then r to the 12 gets really, really, really small, and then the whole thing blows up. And why does that happen? What is that repulsive potential due to? It's due to something called the Pauli exclusion principle. And the Pauli exclusion principle says that no two particles can have all of the same quantum numbers and occupy the same physical space, or orbital in the case of atoms and molecules. So if you look at a plot of the Leonard-Jones potential, you can plot the energy, and what we have is that there's an attractive and a repulsive potential, and at some point we are at equilibrium, and that's where the energy is minimized. Now, what's the force when the energy is minimized? The force is 0 where the energy is minimized. So where the rate of change of the energy is 0, that means it's dW over dr is 0, the rate of change is 0, so the force is 0. So when we're attractive here, then we're repulsive here, and eventually we get to some equilibrium separation, that the energy is 0, the force is 0. So that's how I wanted to wrap up. But that leads in nicely to this video, which is on the effect of adding up the van der Waals forces and how you get attractive and repulsive effects in large particles. So suppose that we have a bunch of atoms in a big particle and a bunch of atoms in another particle, and say these are nanoparticles. Say they have a diameter of like 100 nanometers or 5 nanometers or 50 nanometers. And every single particle in here is going to have a van der Waals interaction with every single particle in here, and we add them all up. And when we add them all up, we get this series of relationships that look a lot like van der Waals forces, except that the energies are dependent on a smaller inverse exponent. So instead of 1 over r to the sixth, we have 1 over the distance between the particles squared or cubed or to the first power. So these forces fall off slower when we have large nanoparticles all the way up to macroscopic surfaces. And then we can get different interactions depending on if we have a sphere and a sphere, or a sphere and a surface, or a flat surface and another flat surface. Keep in mind when you are studying this material that when we have two flat surfaces, we are always talking about the energy or the force per unit area. Okay, so all of those equations where we have flat on flat are per unit area. And it turns out that this flat on flat interaction energy is very useful because if you take two like surfaces, say you take a solid block of a van der Waals solid like sugar, and you just break it right apart and make a flat interface between those two particles, then the force equation tells you the adhesive pressure that you had to overcome in order to break that surface apart. And what we're going to find is that that force is actually enormous. So on the molecular or nano scale, if you pull apart this surface, you get adhesive pressures in van der Waals solids that are close to like 1,000 atmospheres, or 1,000 bars, or what would that be? 10 to the 8 Pascal, something like that. A huge amount of pressure. Now, of course, when we think about taking two van der Waals materials and putting them together and then pulling them apart again, we're not going to get that kind of adhesive pressure. And the reason is because there's a lot of little bumps in that interface. So the interface has to be completely molecularly aligned in order to get that huge pressure, but it exists nonetheless. All right, so there are other forces when we have solutions or suspensions of nanoparticles. Another one is the electric double layer force. And this is a repulsive force, because if we had only van der Waals forces, then everything would be predicted just to clump together and flocculate, and we'd get no stable suspensions like paint and vaccine nanoparticles and coatings and so forth. So the electric double layer force is due to when you put particles that are charged in water, or particles that become charged in water. Say they have an acid or base group on the surface that take on a negative or positive charge, you get a diffuse layer of counter ions around each of the particles. And when you bring those particles close together, that diffuse layer of counter ions gets smushed, and then the big particles push each other apart because of entropy. Why do they push each other apart because of entropy? Because those counter ions that are surrounding these particles like a sphere, like a halo around a sphere, they don't want to be confined. So when you push these nanoparticles or surfaces together, these get pushed apart again. There is another type of before I go there, I want to say that just like in the Leonard-Jones potential, where you take the van der Waals energy and you add it to the Pauli exclusion principle, you get this minus inverse r to the 6th plus inverse r to the 12th dependence, where the 1 over r to the 6th is due to attraction due to van der Waals, and the 1 over r to the 12th is due to repulsion due to the Pauli exclusion principle. Something like that exists for nanoparticles and surfaces, where you have the addition of the attractive force due to the van der Waals force and the repulsive force due to the electric double layer force. So when you add up the van der Waals and the electric double layer force, you have something where you have attractive due to van der Waals and repulsive due to EDL, and with the EDL force is bigger than the van der Waals force, then you have a stable suspension. Or if it's some amount bigger than the van der Waals force. Stable suspension means it's not going to clump up and coagulate or flocculate, as the colloid scientists say. So I'm showing here a picture of the DLVO energy for 3 scenarios, one with a relatively high surface charge density, which gives you a big hump that's labeled barrier to flocculation. Then it goes down as the distance of separation increases. You get a secondary minimum, which is where the particles live most of the time. That's where the energy is minimized. And then if you start decreasing the surface charge density, you go from the blue curve to the red curve. And if you're just listening to me, you're not looking at the picture, that's fine. There's a barrier, and that energy barrier goes down, down, down. And then if you get really close to each other, there's a huge attractive force, because at very small separations, the van der Waals force dominates over the EDL force, no matter how strong the EDL force is. So what you need is a high surface charge density to achieve a good barrier against flocculation or aggregation. The other thing that it's helpful to have is a low electrolyte concentration. If you add too much electrolyte, you end up decreasing the entropic benefit of having a big diffuse double layer. So you add in a lot of salt and that double layer shrinks. And as a result of that shrinking, the attractive force can dominate over the repulsive force, and you end up with something like the red curve, which has very little barrier against flocculation at all. Finally, I want to mention one more thing, and I learned about this because I was reading about milk fat chemistry at one point. Don't ask me why. So it turns out that in whole milk, so this is 3% milk fat milk, the fat is contained in fat globules, where the van der Waals force is very, very strong, and the electric double layer force is not very strong. So you would expect that the milk fat globules would all ball up and coagulate, and you'd get yogurt or something like that, or cheese or something. I don't know which one you'd get. But it turns out that those milk fat globules are stable, and the reason that they're stable is because they have polymers or some biopolymers on the surface of these globules. And those biopolymers on the surface of the globules are sticking out in all directions like a soft star, basically like a star. And if you push those surfaces or particles together, those floppy star-like appendages get confined by pushing these things together, and therefore you get an entropic repulsion. Conceptually, it's quite similar to how the electric double layer force is also dependent on entropy, or also arises due to entropy. Okay. I guess there is one more thing I want to mention, and that's the depletion force. The depletion force involves two kinds of particles, a big particle and lots of little tiny particles. And the big giant particles, which are probably like 100 nanometers, have these little particles around. The little particles could be anything. You could say they're little protein blobs. And so when the big particles get really close together, they exclude the little particles from the gap. Now, why is that a big deal? Because the little particles are constantly bombarding the big particles on all sides. And if you move the big particles together and you exclude small particles from the gap, then the little kicks, the bombardment, the little Brownian motion related kicks from the outside are gonna serve to push the big giant particles in, and there won't be any counterbalancing kicks from the ones in the inside. And that is the depletion force. And that's where we'll end today. I'll see you in the next video.